All right, so this is the last section in chapter 7. Today you'll use algebra tools to investigate the properties of a quadrilateral, and then you will use those properties to verify the identity of the quadrilateral, meaning we're going to name it, and we want to prove that we've got the right name. You just did a job in the quadrilaterals division of your uncle's shape factory. In the old days, customers called up your uncle and described the quadrilateral they wanted over the phone. I'd like a parallelogram with. But nowadays, your uncle says, customers using computers have been emailing orders with lots of different specifications. Your uncle needs your team to help analyze the most recent orders listed below to identify the quadrilaterals and help the shape makers know what to produce. So for each of the quadrilateral orders listed, we're going to create a diagram, and then we're going to decide if the quadrilateral has a special name, showing our reasoning mathematically, and reporting the perimeter of each quadrilateral. So first of all, we have 4 equations. So we're going to start by graphing a +3 for our y-intercept and -3 halves. So down 3, right 2, down 3, right 2. We really don't know where this shape is going yet. So I did draw mine, maybe extending into all of the quadrants, giving myself a little space. The next one has an y-intercept of +9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And also a slope of -3 halves. So 1, 2, 3, 1, 2. So the first thing we notice is at the very least, we have 2 parallel sides. Now we've got an intercept of -3, and our slope is 3 halves. So +3 halves. And we've crisscrossed both of the previous equations, and +3 and a +3 halves again. So we have 2 pairs of parallel lines, so that's interesting. So at the very least, we have a parallelogram. We also want to check to see whether or not we have side lengths that are equal. So this one is up 3, right 2. This one is up 3, right 2. This one is down 3, right 2. This one is down 3, right 2. So in each one of those cases, each one of those sides, the Pythagorean theorem is going to be 3 squared plus 2 squared equals c squared. And all 4 of them are going to come out with the same length for c. We don't actually need to do that just for this part. We would be able to say all 4 sides are the same, 2 pairs of parallel sides, making this a rhombus. But in order to find the perimeter, we do need to do 3 squared plus 2 squared equals c squared. So we have 9 plus 4 equals c squared. And when 13 equals c squared, we would square root both sides. And because we don't want to, round off our number too many times, I would leave it as √3 equals c. So we have a couple choices here. Because it's a perimeter and all 4 sides are the same, we can say that perimeter equals 4 times the length of one side. And we could actually just leave it as 4√3. So the perimeter could be √13, 4 times √13. We also could do the square root of 13, added 4 times, a little tedious, but we could, at some point say, well, that's, 4√13 is not very helpful. So we might do 4 times the square root of 13, and we would say it comes out to approximately 14.4 units. And don't forget it's perimeter, so it's just units and not units squared. So the square root of 13 is approximately 3.6, and then when you multiply it 4, approximately 14.4 units, or you could leave it as 4√13 units. Depending on what you're going to do with the information, one might be more helpful than the other. All right, next, a quadrilateral with these points. So the first thing I did, I already graphed the 4 points. Now I'm going to see whether or not there's anything special or unique about it. It looks like AD might be parallel to BC, so I'm going to check their slope. So AD is rise of 2, run of 4. So that would be a slope of 1/2. And BC is rise of 3, run of 6. So AD and BC both have a slope of 1/2. That makes them parallel. So I might put some symbol for parallel on there. I'm going to also check because segment AB looks like it might be important. And that one has a slope of -2/1. So segment AB has a slope of -2/1, which is the opposite reciprocal. That makes it perpendicular to both of the previous sides, meaning we've got right angles here. So now that I've got that, I have enough information to name this. It has 4 sides, so it's a quadrilateral. I have one pair of sides opposite that are parallel, and that makes it a trapezoid. And because it has the right angles, we would call it a right trapezoid. Other qualifiers would be if we had 2 of the short sides were the same length, you might have an isosceles trapezoid. But in this case, I can see that this side, which is a down 2, right 1, going to be a different length than a down 1, right 3. So they are not going to be equal length. So it's not possible for it to be isosceles. The next thing, though, is finding the perimeter. So on each one of these, I would want to say, for the first one, it's a 2-1 slope triangle, like down 2, right 1. So I'd have 2 squared plus 1 squared equals c squared. So that's a 5. So I'm not going to go any further than that. I'm going to say the square root of 5 equals c on that one. The next one we have is up 2, right 4. So I'd have to do 2 squared plus 4 squared equals c squared. So that's a 20, and I'm going to square root both sides. So I'm going to have the square root of 20 for that side. Side DC is a 1/3. So I'd have to go, 1 squared plus 3 squared equals c squared. Hopefully you're noticing a pattern here, and maybe you can even, do this a little bit more efficiently using the distance formula. Not going to help particularly in this case because the numbers are so small. And last but not least, the bottom was up 3, right 6. So 3 squared plus 6 squared equaled c squared. And we would have 45. So it'd be the square root of 45. And it's not going to be effective or efficient to go typing each one of these into a calculator and rounding them and then adding them. You would want to add the square root of 5 and the square root of 20 and the square root of 10 and the square root of 45. And you would want the calculator to give you one final answer without rounding each one of them. That way you only round once, and it is approximately 16.6 units. And there's no more efficient way to add together all of those numbers that are under the radical symbol. Onto the back, if you had a quadrilateral with vertices at these points, we've got W, which is 0, 5, X, which is 2, 7, Y, which is 5, 7, and Z, which is 5, 1. You'll notice that I've already put in my right angle symbol because I had one vertical and one horizontal. So I did not have to find their slope. I can also see from looking at it that I don't have any pairs of parallel sides. I probably wouldn't bother checking for that. I have, let's see, a single right angle, but having a single right angle doesn't have any sort of special name to it. And I don't have any congruent sides. So this one's just a quadrilateral. Nothing particularly fancy or special or interesting. Last but not least is, so reasoning, I would say, only has a single right angle. Doesn't have anything else to go with that single right angle. We know that it's not a kite because it has no congruent sides at all. Not only does it not have any adjacent congruent sides, it doesn't have any opposite congruent sides. It's got nothing going for it as far as having a special name. I can tell that this is 3 units. I can tell that this side is 6 units without having to do any computation because one is vertical and one is horizontal. But this side here has a rise of 2, run of 2. So I'd have to do 2 squared plus 2 squared equals c squared. And I would get the square root of 8 as that side length, or root 8. And I can label the picture with that if it makes it easier when it comes time to add them together. And then you've also got this one, WZ, which has sides of 4 and 5. You would go down 4, right 5. So you can do 4 squared plus 5 squared equals c squared. 16 and 25, which is 41. And so when you square root both sides, you have the square root of 41. When you go to find the perimeter, you are adding the square root of 8 and the 3 and the 6 and the square root of 41. Again, I would use your graphing calculator, leave everything right on the screen, and go with approximately 18.2 units. Now, I know I did this in a previous lesson, but just to recap, when you're doing this on the graphing calculator, if you're going to do second square root of 8, second does help to turn it on. Second square root of 8, you need to make sure that you press to the right to get out of the radical. So the next one is plus 3, not under the radical, then plus 6, not under the radical, then plus the square root of 41, and then you want to also get the cursor out from underneath the radical, and that's where you get your approximately 8.2 units. A little refresher there in the math notes for midpoint. But I think we're probably okay on that. If you do have any further questions, don't hesitate to ask.